Okay, so the topic we'll cover here is resistivity. Okay, and the first thing we'll look at is we'll just look at what it is that is causing resistance in a wire. That's not really what I want. Actually, this. There we go. So let's just draw a wire, and you'll remember from last time what we were talking about. We were talking about the fact that wires are made of matter, right? And that matter can interact with electrons as they travel through it. Okay? Yeah. Yeah, go ahead. Okay, so if we think about what a metal wire is made of. So this is supposed to represent, the cylinder is supposed to represent a wire, and then what we could say is, let's put a potential across it. Let's make this side negative, and let's make this side positive. So this is just a cross section of a piece of wire, okay? And inside the wire, you have atoms, which consist of a positive nucleus, and around them, you have electron shells, you have closed shells. But if you recall, with metals, you also have valence electrons, and it turns out that there will be, one or two or maybe even three valence electrons associated with each atom, but they don't necessarily belong to a particular atom. And this allows them to be mobile, right? So these electrons can kind of move about, or they just sort of, vibrate and leap back and forth between valence shells, and they're sort of available to move. And this is what gives metals its interesting property, right? Transfer of heat, transfer of electricity, malleability, you can bend this. These electrons sort of act like, if you want, a glue between the positive charges. They're negative, it's positive. So metals sort of are a bit, in a way, fluid or malleable, okay? So as if I put a supply of electrons in, right, we put a field across here, these electrons react to the field, and essentially, they begin to move, all right? However, it's not just free movement. Along the way, there's stuff in there. So if you think of this like a stream, if you think of these like rocks or islands, they're going to impede or resist the flow of electricity through them. Metals have very low resistances, and that's because they have a loose hold on their outer shell electrons. Other types of substances have very strong holds on their electrons and do not allow them to easily flow. These are what we'd be calling resistors or insulators. Okay, so if this were glass or rubber or something like that, these electrons are not mobile, and you have to put a very, very, very large potential across to get electricity to flow through them. If you put a large enough potential across something, you can get electricity to move through it or arc over it. Okay, so I mean, at enough voltage, really any resistance will allow some current to travel. Okay? That's something to think about. So now, how do we talk about this? Well, it turns out that, and this should make sense, the longer a piece of wire is that current has to travel through, the higher the resistance will be. Okay? It's point number one. Longer wire makes higher resistance. Seems logical, right? The lower the cross-sectional area, the higher the resistance. So in a way, you can think of that like a pipe, right? If I have a wider pipe, there's going to be less resistance to flow through the pipe. Okay? So low or narrow wire or really thin wire has a higher resistance than a big fat thick wire. You'll notice if you buy something like an extension cord, the longer it is, the thicker it tends to be, right? And that should make sense. If you're increasing the length, then you're going to have to, that's making resistance quite high, then you're going to have to increase the cross-sectional diameter area of the wire to lower, to compensate for the length of the wire. Does that make sense? And there are like I guess, obviously electrical rules to follow, which I don't really know them. But for X number of length, you need this much width if you're going to run this much current and so on. Okay, there's safety concerns there. If you run too narrow of a wire, right, the resistance is too high, what is that resistor, what is resistance actually doing as this electricity passes through? What's happening across this wire as current travels through it? Right? So it's causing kinetic energy, right, to be transferred into these particles. And remember, when particles contain kinetic energy, how do we sense that at the macroscopic level? What do we feel that as? Heat, right, exactly. So resistance, wastes energy, if you want, by vibrating these particles and emanating this as heat. If there's too much resistance and we're trying to push too much current through, this whole, and if this represents a piece of extension cord, it can get hot enough to melt its casing or cause a fire, right? This is true of household wiring as well, which is why you have things like fuses to cut this off if the current driver gets too high. You don't want this wire overheating and becoming like an element inside your walls, right? That's the cause of an electrical fire. Okay, so that's kind of the basis of what we're talking about, thinking about resistance in a wire. A resistor is, a very thin piece of wire. And there's one more thing we're not considering. What else do you think plays a role in, say, the resistance that this piece of wire is going to have? What's the other thing you think that maybe we haven't talked about yet? Type of metal is also very important. Type of metal or material. By the way, you can make something superconductive. There are ways to make certain materials conduct without any resistance at all. But so far that can only be done really at fairly low temperatures and with pretty kind of exotic materials. If you could find a room temperature superconductor, that would be awesome. Electricity companies and so on, you can imagine, especially in Manitoba, if you think about the fact that our electricity is generated, 1,000 kilometers away from where it's used, you can imagine all that wire strung for kilometer after kilometer after kilometer, emanating heat as the electricity goes, and really just wasting power, right, that we're not getting down here where we are. You could find a way to make those wires superconductive, which I don't know if the laws of physics allow that, but if you could, that would be huge. Yeah. Yeah. Super high voltage. Good question. Yep. 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 Interesting. I'm not sure. I know transformers definitely make a humming noise, um, and the reason why is because they're running on a magnetic system that it's oscillating back and forth with the current, right? And they'll actually like literally physically vibrate because the magnetic field's changing and it's pulling them left and right. You'll often find sometimes with like cheap electronic chargers for like your phone and stuff, you get this high pitched like buzz from them. Yeah, it's the coils vibrating inside at twice the AC power, right? Because they go back and forth. So you get like a 120 hertz ringing, which is super annoying if you're trying to sleep and your charger's buzzing. Does that ever happen to you guys? Oh, you must have better chargers than me. Yeah, yeah. If it's really cheap and like no name, and they haven't like glued the magnets in there properly, it'll buzz. Um, but I don't know about power lines themselves, why they would be buzzing. The super long bipole lines are actually DC, so I don't think you'd get a buzz. Don't quote me on it because I think the current is always traveling in the same direction. But maybe there is something where you have AC current that might buzz. I don't really know, to be honest. Okay, anyway, what I want to get to with this is there's actually a formula that looks like this. So this is resistance equals P, which is a new term, which is resistivity times length over area. Let's just write down what all of this means and how it relates. So this is the resistance in a piece of wire. This is the resistivity, which is a property of the metal itself that the wire is made of, or maybe it's not even metal, maybe it's some other substance, graphite or something. This is the length of the wire, and this is its cross-sectional area. Okay, so units wise, that's meters squared. This is ohms, and this is ohm meters. I'm just going to double check on that here. Okay, so what I've just added here, guys, if you can see, is the resistivity of some selected metals. Okay, the lower the number, right, the less resistance you're going to have for a given piece of wire that is the same in all aspects besides its nature. So if you look, the lowest resistance is copper. There's often some confusion. People are often under the impression that gold has the lowest resistance of any metal. It's not actually true. It's copper. Where I think that misinformation comes from is the fact that in the stereo world, connectors are often gold-plated. That's more to reduce the chance of corrosion on your connectors than it has to do with the conductivity of the materials. So, yeah, in here. Yeah, sorry, it was just pointed out that actually silver has the lowest lowest resistance, or resistivity, I should say. But obviously, there's good reasons why you don't make wire out of silver. For instance, it's very expensive. Yeah. Yeah, I'm not sure. There's probably some other good reasons why. I know it tarnishes, but so does copper. I think like once it's sleeved within its insulator, that keeps air away from the copper, so it kind of prevents it from tarnishing. Yeah. Do you have a question? Yeah, it's 150. Yeah, it's 150. So I don't know why they put that decimal in there. I'm not really sure. Um, that could be. Yeah. Yeah, that could be what. Nichrome. Good question. I think it's a alloy of nickel and chrome based on its name, but I don't know. I know that it's one place it's used is within like stove elements. So there's within that. You think of a spiral element within there. There's a real thin piece of nichrome wire that has high resistance, right? Which is what you want because you want to make heat out of that. So let's just do a quick example question here. Let's see if we can solve something. So, a piece of wire. So let's just is 0.644 millimeters in diameter. What did we say that was? That was AWG 22. Okay, so that's American wire gauge system. It's actually in inches, but we got the conversion. Okay, is copper and has a length of, let's say it's I don't know, 25 meters. Calculate the resistance offered by the wire. Okay, so first things first, we got to find the cross-sectional area. So A area should be equal to pi r squared. So in this case, it should be pi times 0.644 times half squared. So you got to assume there that the assume wire is circular or cylindrical. Generally is. I don't think I've ever seen a square wire. Has anyone ever seen a square wire? Maybe it exists, but I've never seen it. So what we can do with this is we can just say, okay, so we know the resistance is going to be equal to P L over A. I should probably write it all out just right here. So if we go back up, see what copper is, it's 1.72 times 10 to the negative 8. Ohm meters times its length, which is 25 meters. And then I guess we just have to be a little bit careful because this was in millimeters. We should actually probably write it in terms of meters. So 0.644 times 10 to the negative 3 meters. Okay. So 0.644 times 10 to the negative 3 meters. Half of that times pi and square that in there. And hopefully you understand what I just did there. And just give me a sec and we'll calculate what that works out to be. Okay, so I get 1.32 ohms. Okay, what you guys got? Hopefully.